the modern world operates on a fundamental assumption that we know exactly where we are and what time it is at every second of the day. This invisible infrastructure is provided by the Global Positioning System, or GPS. It is the silent heartbeat of the global economy, synchronizing everything from high-frequency stock trades to the navigation of autonomous freight ships and the targeting system of cruise missiles. But GPS is inherently fragile. It relies on a constellation of satellites 12,000 miles above the Earth, sending out signals so weak they can be drowned out by a simple jammer, or spoofed by a sophisticated state actor. In a conflict scenario, the first move of any major power will be to disable or deceive the enemy's GPS. We are currently entering the era of quantum metrology, the end of GPS as we know it, and the rise of the Un-Jammable self-contained navigator. At the core of this transition is the quantum accelerometer and the cold-atom interferometer. While a standard GPS unit looks to the stars to calculate position, a quantum navigator looks inward. It uses a cloud of atoms trapped in a vacuum and cooled by lasers to nearly absolute zero. In this state, atoms behave like waves. When the vehicle they are in moves or rotates, the phase of these atomic waves shifts in a way that is governed by the laws of quantum mechanics. By measuring these interference patterns with extreme precision, we can calculate the vehicle's position, velocity, and orientation without ever needing an external signal. This is inertial navigation taken to its logical extreme. We are talking about a system that can track a submarine or a stealth aircraft for months with centimeter-level accuracy, entirely in the dark. This quantum positioning system is supported by the quantum atomic clock. Current GPS satellites carry atomic clocks based on cesium or rubidium, which are accurate to about 1 second every 30 million years. That sounds impressive, but for high-stakes military and financial operations, it's not enough. Quantum clocks, using optical lattices to trap thousands of strontium or ytterbium atoms, are so stable they wouldn't lose a second in 30 billion years, longer than the age of the universe. This level of timing precision is what allows us to synchronize sensors across thousands of miles to create a single unified virtual sensor. It enables us to detect stealth aircraft by measuring the tiny time delay of a radio wave as it passes through a contested area. It turns time itself into a weapon. The tactical implications of quantum metrology represent a cognitive overmatch. If you possess a self-contained quantum navigator, you can operate in denied environments where GPS has been jammed or spoofed into oblivion. You can maintain perfect synchronization with your drone swarms and satellite constellations while the enemy is flying blind. Furthermore, this precision allows for gravity mapping navigation. Every mountain, valley, and even massive mineral deposits create tiny variations in the Earth's gravitational field. A quantum gravimeter can map these variations in real time, matching them against a high-resolution gravity map of the planet to determine position with absolute certainty. This is a navigation system that doesn't just work without satellites. It works through solid rock and deep water. For the hardware developer and the military strategist, the shift to quantum metrology is a race for a positional sovereignty. The nations that build the first reliable portable quantum navigators will no longer be dependent on vulnerable satellite networks. They will have a fleet that is invisible, silent, and always knows exactly where it is. We are moving toward a world where signal interference is a thing of the past, and where the most secure place to be is completely off the grid. The end of GPS is not the end of navigation. It is the beginning of a world where we no longer have to look at the sky to find our way home. We are finding our way by looking at the fundamental vibrations of the universe itself.